Here is a standard Blender rigid body physics simulation, and it looks fantastic. I love it. The only thing I don't love about it is how little control I have over when it happens. Yes, if I was certain I wanted my box to collapse on frame 112, I could start the simulation there. But what if I wasn't certain? Stepping back, what if I didn't want to have to be certain? Wouldn't it be convenient, having baked these lovely physics, if I had some kind of non-destructive system that could give me quick and flexible control over the playback, so that I could activate it at any point on the timeline, at any speed, in any direction? Well, I have built that system in geometry nodes. It is the identical physics simulation, but what happens here is we control the playback of it. So let's say I wanted it to start frame 30 and have finished by, I don't know, frame 100. So I plug in the values, press play, it starts at 30 and it's done by 100. Okay, what if we think I'd really like it to start a bit sooner, like maybe frame 20, and I want it to go faster. I want it to end faster. So let's take the end down to 60. There we go, starts at 20 and it goes faster. What if we wanted to do backwards physics like that? Well, think about it. Backwards physics would just be physics where the start is towards the end and the end is towards the start. So if we just invert these two values, say we start on frame 60 but we end, paradoxically, on frame 20, then we have backwards physics like that. Now, easily controllable backwards physics, if you have ever tried to do backwards physics by conventional means, you should appreciate how nice this system is by contrast. But really, the fun is only just getting started, because what if I didn't want to use a global time parameter to control the beginning and end of the simulation? What if I wanted to use something like a local spatial influence? In this case, the box is falling up and down, the physics are going forwards and backwards, driven by the proximity of this empty. And this is exactly the same node tree, exactly the same system as the timed one, just with a different controller mechanism. And the system itself, the geometry nodes, is surprisingly lightweight. Let's have a look at it here. Yeah, it's not very big. It's not very many nodes. And so it shouldn't take too long to build and to show you how it works. I won't say it's lightweight and it's not many nodes. It's not exactly straightforward. Nonetheless, I would like to try and make this tutorial beginner-friendly, by which I mean I will put screencast keys here so that if a beginner wants to, they can at least follow my steps and end up with this animation. The explanations might go a little bit over a beginner's head, but you know, that's life. Let's get started. Okay, in a fresh Blender scene, the first thing I'm going to do is select the light and the camera and get rid of them because they can be annoying and might get in my way. I'm now going to select our default cube, go into edit mode, and move it down by 1 meter so that the origin is now at the top. I'm going to scale this up considerably and then scale it down on the Z because this is going to be our floor, and we don't want pieces of the cube falling off. We want, you know, too much space. So let's apply the scale. Let's rename it to floor, and while we're doing some housekeeping, let's turn on, well, you don't have to do this, this is personal preference, but I find cavity both can make things really nice and legible. Okay, let's add another cube. This one, let's move up in object mode 1 meter. And because I am superstitious, I'm just going to move this up a tiny bit because I don't want collision problems. let's take our cube. We're going to cell fracture this thing to get it into fragments. To do that properly, we need to give it some more geometry. So let's go into edit mode, subdivide it once, twice, 3 and 4 for good luck. And simply because I think it looks cooler when fragmented, I am going to, rather than have a solid cube, I'm going to have a kind of hollow cube, which use a solidify modifier, and I'm going to go into X-ray view so I can see the thickness of the thing. And make it a bit thicker. Yeah, something like that. Should be just fine. Out of X-ray view, go to Object, down to Quick Effects, to Cell Fracture. If you're a beginner, you may, and you haven't enabled this already, you'll have to go into Preferences to enable Cell Fracture. So hit Cell Fracture. The standard settings should be fine for this. About 100 particles sounds fine, so hit OK, let it do its thing. And when it's ready, without clicking away from it, hit M to move all these pieces into a new collection, and we'll call that collection static. Create. Again, without clicking away, hit Shift D to duplicate all of the pieces, right click to confirm, hit M again to move them into another new collection, this one called physics. Okay, so I'm going to just for now disable both static and physics. We don't need the original cube anymore, so let's get rid of it. Now, before we move on to the physics, I have to point something out. If you have your own physics system, or your own objects with physics, you're going to have to assemble in the same way two identical collections for them. One static with no physics, and the other which will have the physics. And what's critical is not only that they have the same contents, but that the contents be in exactly the same order. So when we ran the cell fracture, it will have made the pieces and then given them an order, and who the hell knows what the order is. Let's just find out where the first one is. Okay, so it's down here. So keep that in mind. We'll unselect and disable the static, enable the physics, and let's look at the first piece in the physics collection. It should be in the same place. Lo and behold, it is. Great, perfect. This is critical. These two collections have to be aligned in terms of indices. If you have different objects, I don't know, you could have plank 17, chimney 43, or whatever. I mean, if that's kind of your naming convention, and you duplicate, all of those objects would have to go into a collection, and then if you duplicate that collection, I have found that the indices can get jumbled, which is a disaster from the point of view of what we're doing today. What I would recommend doing is assemble all the objects into a static collection and then batch rename them by hitting Control F2. So call them, I don't know, piece 1 or piece 0, piece 1, piece 2, whatever. And then duplicate that collection, and the indices should work out just fine if you've done that. Okay, let's move on to our physics. Making sure that none of the static collection is selected, because you don't want to accidentally apply physics to the static pieces. So we've got nothing there. Good. We'll disable that again. Go back to the physics. Pick a piece that you like. Any piece. I want this one. Go to Object. Down to Rigid Body. Add Active. Now, if we look at the settings, these standard settings are fine. Convex hull will be just fine for this purpose. What we now do is select all of the objects in the physics collection by right-clicking on the collection and hitting Select Objects. Now you should see the one that you had previously selected, the active, this guy, is kind of outlined in yellow rather than orange. This is what we want. If for some reason it's become deselected, you just need to shift select it to get it. So that we can now go to Object, Rigid Body, Copy from Active, which gives all of the pieces the same physics settings. Okay, so I'll deselect them. Before we run the physics simulation, let's go over here to Scene Properties, down to Rigid Body World. The standard setting is a speed of 1, and what I recommend doing here is slowing this down a bit. The reason we do this is to have more time resolution. If we don't have enough of this, then some of the animation can stutter a bit. And you could use a setup like this for some kind of, slow down, speed up bullet time effect. And if you were going to do that, you would need a really high time resolution. So you would have to put a really low speed here and then do the simulation. And then later, with the geometry node setup, you could vary that speed. Okay, so you know. So for this effect, a speed of 0.5 will be just fine. Now, before we run the simulation, let's make sure that the floor also has a rigid body, in this case, a passive, and convex hull is just fine. Let's hit space. Yes. Okay, I like that. I'm happy with the way these pieces have all landed. So what I'm now going to do, whilst staying on this frame, is select all of the objects in the physics collection, again by right-click, select objects, go to Object, down to Rigid Body, and say Bake to Keyframes, and then, I'm satisfied with the way it looks on 113, so I just want to bake from 1 to 113. Say OK. Let it do its thing. Don't panic. Don't quit Blender. It's just going to take a minute to do this. Go and have a snack. Okay, it's done already. So now what we have is the simulation baked to keyframe. So for any particular part, fragment, we can just have a look at it, and we can see, if you look at its location and its rotation here, if we inch forward, we have all of that data stored really solidly here. And I'm not sure that you'd have to do this, but it feels like tempting fate not to, because we're going to run another simulation on top of this, and I just want to have this in as solid a form as possible, because as I said earlier, I am a bit superstitious. Okay, let's build the node. Okay, first things first, let's disable or unclick both static and physics collections. Here, let's add a container object for our geometry nodes. A plane would be just fine. Let's rename it to something or other, like maybe physics controller. And ordinarily I would do geometry node stuff over here in that tab, but I've been having difficulty getting the screencast keys to work there. So I am going to open a new window here. You can do it wherever you like, but it'll be the same, but just so you know why I'm doing that. What do we want? Geometry node editor. Okay, let's add a new geometry node to it. We do not need the group input. Let's get rid of that. And let's bring in our physics collection. And let's hook it up. And if we press the spacebar, we'll see it plays. Okay, what do we want first? This bake that we have up here, we essentially want to import it into geometry nodes in a way that will be legible, that we can later read. So let's take a noodle off. Oh, and by the way, separate these children. Let's take a noodle off the instances and type ITP, because we want an instance 2 points. If you know the name of a node, if you can type its abbreviation, it usually comes up. So instance 2 points, not instance on points. And what we want is a simulation zone. we now want a join geometry inside the simulation zone, and we'll want another join geometry up here to join the points to the instances. So plug that in. And now, if we plug the instance to points into this join geometry, if we press play, we'll see that each instance leaves behind it kind of a trail. This is half of what we need, because on these points is stored the position of each of the fragments on each frame. So yeah, that's half of what we need. We have the position. I mean, you can see we have the position because they're in the right positions. We'll also need the rotation data of each of the instances. To do that, make some space, we're going to need to capture an attribute, namely the instance rotation. And this needs to be captured on the instance domain. So we plug this in. Having captured it, we need to store it here on the points. So we want all of these points to be where they are, but we want the corresponding rotation data also to live on these points. Easy enough. Let's get a store named attribute. Let's put it here. It is on the point domain because we're now dealing with points. That's fine. It is a quaternion because it's a rotation. And let's call it rot, because it's always fun to call rotation rot. And let's plug in from the capture attribute over here to the value. So you might think this would be enough. Oh, we've hooked it up now, so the data's there. It's not. We need to kind of play it again to get this into the simulation zone. And this feels really silly because very few things in Blender are kind of dependent on skill of execution in this way. But what we have to do is go back to the beginning, hit the spacebar to start it, and then as soon as the physics simulation is done, hit spacebar again to stop it. If I recall, there were 113 frames worth of stuff. So on frame, not before, but not too long after frame 113, I want to stop this thing. So start, and how am I going to do? Oh, not too bad, 116. Okay. We now have the points, and they now have the rotation data on them. What we need to do now is to bake this. So let's get a bake node, stick it on this noodle. And you might think that we would want an animation here because, after all, it's a physics simulation, which, you know, it animates. No, we want a still because we want to bake essentially a lookup table here so that at any frame we have access to the position and rotation of any fragment at any other frame. And the way to do that is to bake it when it's complete, and so we can then go back in the timeline and it'll still be there. So with still selected, click bake. And there we go, baked on frame 116. Now we can get rid of the instances themselves. What we are going to do is take our other collection, our static collection, and move it according to this information that we've now stored over here on these points. It's not that easy to visually demonstrate how the indexing works here, but it's a lot easier than you might think. As a basic principle, this point, I have no idea what this index is. What I do know is these points inherit the indices from the collection that they were baked from. So every frame they bake in the same order. So however many of these there are, it'll bake this point, and then to get to the next point, the next frame of the animation for that fragment, all I need to do is add the total number of objects in that collection to that index, and it has to be the next one. So index n plus number of objects in collection will be the index of the next one. If I wanted to say get 5 frames ahead, I would just need the index plus 5 times the total number of objects. So it's not actually that complicated, and I hope you'll take my word for it. We don't actually need to see these things anymore, so let's disconnect that and let's bring in a static collection. Separate the children again and hook this up to the output. These are the pieces we want to move according to this information. To move anything, or mostly to move things, we use a set position. And what we don't really need that giant geometry, do we? What we need to do is to sample the index from here. So drag out a sample index node. First off, let's get the positions. So it's on the point domain, and what we're looking for is a vector, the position. That was the easy bit. The index is a bit tougher. As I said, we know that the next frame for any given piece will be index plus total number. That total number is also known as the instance count. So all we need to do is get a domain size out of our static collection, set it to instance, and this will tell us that number. So what we need to do is take this instance count and multiply it. Now it always has to be multiplied by an integer, by a whole number, because whatever, 2 times the instance count will be 2 frames along, but like 1.5 times the instance count will be someone else's, a different fragment's position data and rotation data, and it will be a total catastrophe. So bear in mind, this number it's multiplied by has to be an integer. We could just get an integer node and do it that way, but there's a reason that I'm going to get a value node first and put it into a floor. What this will do is whatever value we have here, this will only return the integer part of it. It'll ignore everything after the decimal point. Okay, so we have this, and now all we need to do is get our index, which in context is the index of these static pieces. And this is a bit awkward. I need to make some room. We say index add this value, and this goes into the index here. And now all we need to do is hook up this sample index into the position, and we'll see, okay, something's happening already. We'll see as we move this number, that's the positions. And yeah, we haven't got the rotations yet, but this is halfway. Fantastic. All we need to do for the rotations is follow the exact same indexing logic. And in fact, the easiest way to do this is to get this sample index, duplicate it with inputs by saying Control-Shift-D, disconnect the position from the value. We want a different value, but we want exactly the same index because we want the corresponding rotation data for every position point. And so this time what we're after is a quaternion. Also on the point domain, what did we call it? We called it rot. So you should be able to add a named attribute. Hopefully, if I just click it, this will be a drop down, and yeah, there's rot. If this doesn't turn up, you can just write rot, and set this to quaternion, and it'll find it. Okay, so this, instead of position, we use the rot, it goes in there. And how to update the rotation of the piece itself, we use a rotate instances node and plug this into here. And now we'll see if we shift around our value, we have our physics simulation. And what we'll see, yeah, there we go. If you go above or below the number of frames that we have baked, everything will zip to 0 because we're sending it to non-existent indices. So this has to be limited between 0 and what you would think of as the wherever you got to with this, baked frame 116 in my case, -1, because in indexing language, this is 115. Take my word for it. So if you wanted to have a kind of global time controller for this, the first thing I did in the overview, it's very simple. All you'd need is a scene time node. You'd get the frame into a map range, and from min and from max are the frames to start and end the physics. So I don't know, let's say 20 to 70. And this is a little bit confusing. You'd think you'd go from whatever it is, 0 to 115. The way the indexes stack in this is they don't stack up like that. Every new frame kind of pushes all of the rest forward. So in indexing terms, it means the very first frames are all the way at the end of the lookup table. So we kind of have to go backwards here. So this range to whatever we have as a maximum -1, n -1, so 116 -1 is 115 to 0. And if we now plug this into the floor, and the floor is still absolutely essential, and go back to the beginning of the animation, we'll see that at frame 20 it should start, and by 70 it should be done. Yep, that worked. And if you if, like in my overview, you'd like to have external control of this over here, it's very easy. All you need to do is add a group input and promote the from min and from max to group inputs, and you can go over here and say start and end. Excuse you. End. And you can and then you can control it that way. I'm going to move on now to the proximity version of this, so I don't actually want these. So I'm going to get rid of them, and I'm going to take them off the group input. Get rid of that. In fact, I don't need this at all. So to have a proximity version, first we need something for it to be proximate to. So let's add an empty. This is a matter of personal taste, but I happen to like the sphere empty because I can see it very well. And I'm going to move it just up the y-axis by gy. There we go. I don't want to move on the x-axis yet, and that should kind of become clear soon why that is the case. So to do this, all we need to do is, okay, I guess we should be building this. Actually, you know what? Let's get rid of that. We should be building this over here. We need the position, which in this context means the position of all of these pieces. I am not interested in the Z component of the position. In fact, I want this proximity effect to act as if Z didn't exist. It's going to be a 2D gradient. So to do that, I'll just multiply the position by 110, which basically crushes the Z component. And we also need the location of the empty. So let's just bring in the empty. Original should be fine. And what we're interested in is the distance between this and this. So let's get a distance node. Let's plug the location into the bottom socket. And once again, we want to map range this value. And what I'm going to say is from 1 meter to 4 meters, which in effect means 1 meter or less, or 4 meters or more. I'm going to say when it's close to near 1 meter, I want it to be fully assembled, which means the first frames, which means the later indices, confusingly. So what was that? It was 115 in my case. And from 4 meters or more, I want it to be 0. Now, if I plug this into the floor and then get my empty, and if I move it along the y-axis, you can see, hey, this happens. It was very satisfying to me. I really like this. Okay, so we can keep working on this. I'm going to quickly just keyframe the empty to move so I don't have to do it manually. So I'm going to go back to the beginning of the timeline. I'm going to say about 160 frames is what I want. Bring up, I'm going to keyframe the empty's location. I'm going to put it somewhere where all of the pieces are definitely all the way down, like there. Put in a keyframe, go halfway along the timeline, so to 80, go all the way to the other side of the Y, similarly to where they're all finished. Put in another keyframe there, and now I can just duplicate the first keyframe and stick it at the end. And what this will mean is now this thing is just going to go backwards and forwards, and we can keep working on the notes. And it's very, very nearly finished. Oh, and I should say, by the way, you could also, go on the x-axis for this. You don't have to do it along the y. You could do it along both. You could have some really exciting thing. Anyway, so it's very, very nearly there, but there's one little kind of bug to it, which is if you look at the outmost pieces, the furthest ones out, the rotations are a little bit dodgy. They kind of stick into the ground and then they snap at the end. The reason this is happening is the distance here we're looking at is not the distance between the empty and the static positions of the cube up here, but the kind of live positions which have been displaced, and this causes a bit of bugginess. So we can fix that. All we need to do up here, on our static instances, before the set position, is store a named attribute, and this will be on the instance domain. Domain. Thank you. Instance, and it will be a vector. And what it is just the position. So this is the pre-displaced position. And let's just call it spos, meaning static position. And now, rather than use this position here, we can get a named attribute. And hopefully, if I click, yeah, there it is, spos. If we plug this in here, rather than the position, we'll see, look, I don't know, look at a glitchy point. Bing! There we go. Okay. So, yeah, it works. That's about it. I hope I hope this has been understandable. I hope you enjoy this and you have fun with it. If you make something with it, tag me. I am curious to see what people might do with it. Yeah. Happy Christmas if you care about that kind of thing. Peace.